Alright, welcome back to another video on my channel, math_exe. Today we're going to look at special quadrilaterals and polygons. So for the special quadrilaterals, I would talk specifically on their angles and their relationships between possibly the diagonals of the quadrilaterals and stuff like that. So anyways, the first special quadrilateral that I'm going to talk about is the square. So we all know that a square has 4 equal sides, and it also forms right angles at its vertices as shown right here. But it also has 2 pairs of parallel lines. So if I draw another square, you can see that this line is parallel to this line, and then this line is parallel to this line. This property is uncommonly taught in possibly books and stuff. However, it can be easily seen from this diagram right here. And the next thing I'm going to talk about is its diagonals. So its diagonals looks something like this. So something about the diagonals is they bisect each other. So what I mean by bisect, it means that it divides a line segment into 2 equal parts. So this diagonal, I'm just going to call this diagonal D1 and this diagonal D2. So diagonal 1 bisects D2 into 2 equal parts, and then diagonal D2 bisects D1 into 2 equal parts, and these 4 diagonal line segments are all equal. It also bisects each other at right angles. So this is a right angle, this is a right angle, and so on. And one last thing to mention about the diagonals of a square, is that it bisects the angles as well. And what I mean by bisect in this context is it divides. So I'm just going to draw a line segment right here and a diagonal. So we know this forms a right angle. So actually this diagonal actually divides this angle into 2 equal parts. So this part will be 45 degrees and this part will be 45 degrees. They all add up to 90 degrees. So yeah, that's it. So that's it about the square. Now we're going to talk about the rectangle. The rectangle has 2 pairs of not only equal but is also parallel, as you can see in the diagram right there. And of course, it also forms right angles at its vertices. So again, like the square, I'm just going to talk about its diagonals as well. So the only property that the diagonals of a rectangle has is that it bisects each other, just like the square. That means the diagonals cut each other into 4 different parts right here, and they are all equal. So that's it for the diagonal of a rectangle. Now the next thing I'm going to talk about is the parallelogram. And as the name suggests, it has something to do with parallel lines, and it has 2 pairs of them. So it is this pair marked in blue, and this pair marked in green. So not only they are parallel, that it also says that opposite sides, which are the parallel lines, and I should have said any parallel lines must be equal. So this green parallel line must be equal to this green parallel line, and so as the blue parallel lines right there. And it also says that opposite angles, and for this I'm just going to draw another parallelogram. It says that opposite angles are equal, and what I mean by opposite angles, I mean angles that look like this. So this blue angle right here and this blue angle right here are opposite angles, and they are said to be equal. Likewise, this right angle with this right angle must be also equal to each other since they are opposite angles. And last thing to mention about parallelograms is its diagonals. So I'm just going to draw another diagram for configuration. So its diagonals look like so. And they bisect each other but in a slightly different way. So this diagonal I'm just going to call this D1. This diagonal I'm just going to call this D2. So D1 bisects D2 into two parts, and it should be said two equal parts, and then D2 bisects D1 into two equal parts. However, you must be careful about this because all these four parts are not equal to each other. They are in form of pairs, and those pairs are equal to each other. The next thing is the rhombus, and basically a rhombus is just basically like a parallelogram, but it has four equal sides instead of two pairs. So all sides of a rhombus must be equal. And like in the parallelogram, it has two pairs of parallel lines, which are those which is marked in green, and those which is marked in blue, like here. And like the parallelogram, it says that opposite angles are also equal. So I'm just going to draw a rhombus. This is not exactly a rhombus, but just assume it is. So we have blue angles right here, and these are red angles. So opposite angles are pairs of angles that looks like this. So they look face to face at each other. So this blue angle must be equal to this blue angle since they are opposite angles, and likewise the red angles as well. And for the diagonals of a rhombus, which is like this and like this, and although this may seem to be incorrect, they actually bisect each other at right angles. So all of these are right angles. And just like the parallelogram, the diagonals bisect each other into two pairs of equal parts. So this bit must be equal to this bit, and this bit must be equal to this bit. And one last thing, I'm just going to draw another diagram of a rhombus. It is something that has to do with angles. So we draw this these diagonals right here alongside with these angles right here. So actually these two diagonals actually bisect the angles. And what do you mean by bisect the angles? Just like the square, it divides the angles into two parts. So in this angle, this bit shaded in red must be equal to this bit shaded in green, and likewise all the other angles as well. So that's it for the rhombus. And the second last one is the trapezium. The trapezium has a pair of parallel lines as seen right here. And if you are familiar with the special angles in parallel lines, you may know interior angles, or sometimes called co-interior angles, which says that any angles that form in this line segment pattern right here, it looks like a C, but sometimes it could be a backward C. Those angles which form in that line segment must add up to 180 degrees. So from this diagram, angle A plus angle D must be equal to 180 degrees, and likewise angle B and angle C as well. And that's actually it for the trapezium. Now finally it is the kite. The kite looks something like this. So as you can see here, it has two pairs of equal sides. So this bit and this bit and this bit and this bit. And it also has a pair of equal opposite angles, which is this part and this part. And keep in mind, this angle and this angle is not always the same, or I would say not generally the same. However, it could be the same if this kite is a rhombus. However, we're going to assume that it is not. So, like the other, like most of the other shapes, I'm just going to talk about its diagonals. Alright, so I'm just going to draw another diagram for this. Apologies for my bad drawing. So we have this and this diagonals. And first, you may notice that these diagonals intersect at right angles. And the last thing about these properties of diagonals is that they bisect the angles. However, they only bisect a pair of angles which are opposite to each other. So as you can see, angle B and angle D are opposite angles and are bisected by this diagonal right here. So as you can see, this bit, which is B1, angle B1, and this bit, angle B2, must be equal to each other. And likewise D1 and D2 as well. So that's just a brief explanation for its properties of special quadrilaterals and all about its angles and stuff. Now we're going to look at polygons and what they necessarily mean. So the word poly means many. That means the word polygon means a shape with many sides. So yeah. And another term that you need to be familiar with is regular polygons. So a regular polygon is a polygon that has the properties that all sides of the polygon must be equal, and all angles, and what I mean by angles is the interior angles, which I'm just going to explain a bit later, must be equal. So speaking of interior angles, I'm just going to talk about interior and exterior angles. And you must differ this from interior angles in parallel lines. And what I mean by interior angles in this context is the angle inside the polygon as shown right here. So a way to remember it is by knowing that interior starts with in, and in just means inside, so it means the angle inside the polygon. And then we have exterior, and likewise x means something outside, so it is the angle outside right here. And notice, the first thing you may notice is that the interior angle and the exterior angle are both supplementary angles, and what they mean is they add up to 180 degrees like so. Now there are some certain formulas you must be familiar with, which is First, a pretty common one, which is the sum of all interior angles in a polygon with n sides, where n is an integer, specifically positive integer. So it's given with this formula right here. So we have n minus 2 times 180 degrees. And this is true for all n equal to or greater than 3 and positive integer values of n. And why it must follow this rule? Well, if you think about a polygon with two sides, you might not be able to draw anything with two sides. It leaves this open area right here. And likewise, it also works for like negative one sides. I mean, it doesn't make sense for a polygon to have a negative one sides, or possibly the root 2, the square root of two sides, or something like that. And we have the size of each interior angle of a regular n-sided polygon, and I texted regular in caps lock because, well, this is pretty specific for regular polygons, so you must differ polygons between regular polygons and irregular polygons. So it is given with this formula. The size of each interior angle must be equal to n minus 2 times 180 degrees over n, which is just the sum of the interior angles over the number of sides, or the number of angles the the number of angles the polygon has. And like the rule above, it must satisfy these rules right there. And for exterior angles, the sum of all exterior angles in an n-sided polygon must be always equal to 360 degrees. Doesn't matter if it's regular or irregular. And finally, the last formula is the size of each exterior angle of a regular n-sided polygon is given by 360 degrees over n. Alright, so that's it for the special quadrilaterals and polygons. And I'm just going to work out for some examples. And for the first question, we're just going to start things off very simple. So in the figure below, ABCD is a parallelogram with AP equals AD. And then we need to find the values of the angles W, X, Y, and Z as shown in the diagram below. So if you know the characteristics of the angles inside a parallelogram, you probably want to find Y first. And that is pretty simple because it says that opposite angles in a parallelogram are equal. So what I mean by opposite, it means that they must face each other. And since y and 80 degrees must be equal, that means y must be equal to 80 degrees as well. And then we have x. Now notice that the triangle ADP is an isosceles triangle. And what that means is this angle marked in yellow must be equal to this angle marked in yellow, and the angle of a individual yellow angle must be equal to 180 degrees minus 80 degrees divided by 2, which is 50 degrees. And from here we can just find the value of x, which is just 180 degrees minus 50 degrees, which is just 130 degrees. So we've found x, which is 130 degrees. Alright. And then from here we can just find w as well. And that notice that even though I didn't say this, since we know that AD is parallel to DC And by interior angles, I'm just going to mark this angle in yellow. By interior angles in a parallel line, angle Y and this angle marked in yellow right here must add up to 180 degrees. So since we know Y is equal to 80 degrees, we know that this bit of this this yellow angle must be equal to 100 degrees. And therefore we can just find the angle of W, which is just 360 degrees minus 100 degrees, which is 260 degrees. So we found W, which is 260 degrees. And from here we can just find the Z by noticing that the quadrilateral BCDP, well, we know this is a quadrilateral, and therefore the sum of its interior angles must sum up to 360 degrees. So from here we can just find Z right away. So Z must be equal to 360 degrees minus 100 degrees minus 130 degrees minus 80 degrees. And you can just calculate this to get the final answer of 50 degrees as well. Or possibly a simpler way is, notice that since we know that opposite angles are equal, we know that this 100 degrees must be equal to this whole bit marked in red. And since we know this little bit is 50 degrees by the isosceles triangle before, then this bit which is Z must be equal to 100 degrees minus 50 degrees, which will also leave us in the same value. So these are the answers for question number 1. Right, so here's the second question. It says the figure below shows a regular hexagon ABCDEF and straight lines BAG and EFG. So we need to find the values of P and Q. Now first, it's probably obvious to find the value of P by noticing that ABCDEF is a regular hexagon, and we know that a hexagon has 6 sides. That means we can just use the sum the size of each interior angle in a regular hexagon, or I should say a regular n-sided polygon, which is 180 degrees multiplied by n minus 2 over n. And since we know n must be equal to 6, since it is a hexagon, we can just get this value, which means that each interior angle must be equal to 120 degrees, which in fact is the value of P as well. So in fact, we found our first value of this. And for Q, you might just want to label some more angles to make this a bit more obvious. So since we know P is 120 degrees, this bit must be equal to 120 degrees as well, as well as this bit. That means this angle and this angle marked in red must be equal to 60 degrees and 60 degrees. And since we know the sum of all angles in a triangle must add up to 180 degrees, we can just find quickly that Q must be equal to 60 degrees as well. Alright, so that's it for question 2. Let's jump into the third one. Alright, for question 3, we need to find the values of A, B, and C given this diagram right here. And usually in these types of problems, you need to just focus on a single diagram, or maybe a single part of this sketch of diagram, so that you can just find each part pretty easily. Alright, so first let's just solve for A. And we can just notice that from the segment, let's see, FEPB, it looks like a Z right here. and we know that these and these segments, lines are equal, and this is 43 degrees and this is A. And by alternating angles, we can just quickly conclude that A must be 43 degrees. Looking good so far. Next, we can just find B by doing the same trick by using alternating angles, but we're just going to look at the segment EFBP, which looks like an inverted Z. This angle is 47 degrees. And again, by alternating angles, this angle must be equal to 47 degrees. And you can just use vertically opposite angles to find that angle EFB must be equal to angle AFG. So since I'm just going to run out of space in this diagram, I'm just going to draw another one right here. Slightly bigger. So I'm just going to plot all the clues and steps that we have done so far. So we know by vertically opposite angles this must be equal to 47 degrees, and this angle is B. And since all angles in the triangle is 180 degrees, we can just find B, which is equal to 180 degrees minus 100 degrees minus 47 degrees, which is 33 degrees. So we found our second value, which is 33 degrees. Now next we're going to find C, and solving C needs something to do with parallelograms and opposite angles and stuff like that. So first we can just have our first clue for C by looking at this segment AB and AP and PC. And since we know AB is parallel to CP, and we know B is 33 degrees, and this segment by alternating angles must be also equal to 33 degrees. And then we can just find this angle right here. Since GFE is a straight line, we can just find this angle, which is 132 degrees, or by noticing that adjacent angles, what I mean by adjacent angles is angles that are next to each other in a parallelogram must be equal to 180 degrees. So that's just a side note, even though I didn't written it on my notes in the first clip. And by opposite angles in a parallelogram, this 132 degrees must be equal to this whole thing right here. And solving C from here will just be pretty straightforward, since you can just subtract 133 degrees by 33 degrees and 43 degrees, which then will lead us to an answer of 57 degrees. And let's just double check that, and yep, the answer is indeed 57 degrees. So these are the answers for question 3. So that's question 3. Let's jump into question 4. Alright, so here is a triangle PQS with QRS is a straight line and PR is equal to QR. And we need to find the unknown values of X and Y. Alright, so first we can just notice that the triangle PQR is an isosceles triangle, given the equal legs on PR and QR are equal. And since we know this angle is 7x minus 3, this angle must be also equal to 7x minus 3 degrees. And just a quick tip, when you are solving these type of problems that contains like a certain expression containing variables as an angle, we can just try to build a relationship. For example, just like forming a triangle with all the all the angles being the expression in that single variable, and then therefore after that we can just form a linear equation and then solve for the unknown variable after that. So in this case, we're just going to do exactly that. So secondly, since first we know that uh, triangle PQR is an isosceles triangle. So secondly, since this angle is 11x minus 6, this angle right here must be 180 degrees minus 11x minus 6 degrees. So since we know the sum of all angles in a triangle is 180 degrees, we can just form a equation like so. So we have 7x minus 3 degrees plus 7x minus 3 degrees plus 180 degrees minus 11x minus 6, 11x plus 6 degrees is equal to 180 degrees. So we can just simplify this real quick. And I'm just going to cross each degrees out here just for simplification. So this inside here will become negative 11x and plus 174. So to 180. And therefore we have 3x is equal to, now we need to calculate this. So we can just subtract 174 on both sides and then add 6 after to get the right hand side being 12, and then x is equal to 4. There we go. So we have x equals 4 as our solution. And solving for y is also pretty simple, since we can just substitute x equals 4 into each expression right here. So this angle will just be 60 degrees, and this angle will just be equal to 50 degrees. And therefore, we can just immediately notice that y must be equal to 180 degrees minus 60 degrees minus 50 degrees, which will leave us y is equal to 70 degrees. Alright, so that's question 4. We have 2 questions left. So let's jump. Alright, so this figure below shows a part of a regular n-sided polygon, which has vertices A, B, C, D, and so on. I put dot 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 right there because we don't know the value of n yet, and therefore we can not determine the number of vertices this polygon has. We're just given a part of it with this angle right here being 12 degrees. So we need to find the angle ACD, which is this angle right here, as well as the value of n. So first, notice that this polygon is a regular polygon, and that means all sides in this polygon must be equal. So this side must be equal to this side, which is equal to this side, which is equal to this side, and so on. However, we're just going to look at this specific diagram right here, which is indeed a isosceles triangle. So this is 12 degrees and these legs are equal. And since we know this is an isosceles triangle, we can just quickly note this is 12 degrees as well. And then we can just find this to be 180 degrees minus 12 degrees minus 12 degrees, which is 156 degrees. And then again, knowing this is a regular n-sided polygon, all angles and I should be set all interior angles in this polygon must be equal. So since we found this to be 156 degrees, this whole bit must be equal to 156 degrees. And for diagram before, we know this angle is 12 degrees, and therefore we know that this green angle must be equal to 156 degrees minus 12 degrees, which is 144 degrees. Alright, so finally to find the value of n, and we can just use the formula for the size of each interior angles in a n-sided polygon, which looks like this. So if you form an equation, it will look something like this. However, this looks pretty complicated, and I'll just let you guys work this out by yourself. I'm just going to work out the exterior angle of this. So the exterior angle of this is just 180 degrees minus 156 degrees, which is 24 degrees. And since we know this is a regular polygon, then all exterior angles must be equal to, well, 24 degrees. They are all equal. The exterior angles are also equal. So with this, we can just use the formula for the size of each exterior angle in a regular n-sided polygon, which is 360 degrees over n. And since we know this is 24 degrees, and then quickly solving this, we can just get that n is equal to 15. So in fact, this polygon has 15 sides. Alright, so that's question 5. Let's jump into the question 6, which is the last question. Alright, so here's the final question. ABCD is a kite with diagonals AC and BD. And we need to find the angle BCD, which is this angle right here. And we need to find the reflex of BAD, which is this angle right here. So first, it's pretty obvious to find angle BCD first. And first, you must notice that since this is a kite, it has two pairs of equal angles, which is this and this, and this and that. And we're just going to look at the triangle BCD formed right there. So we know these are equal. This is vertex D, this is vertex B, and this is vertex C. And we know this is 52 degrees as well. Alright, so notice that this triangle is an isosceles triangle. That means this other angle must be equal to 52 degrees. And from here, it's pretty obvious to find the angle BCD, which is this one right here, which is just 180 degrees minus 52 degrees minus 52 degrees. And when you work this out, you get, I'm just going to calculate this real quick, you will get 76 degrees. Alright, so that's the first part done. We need to find the reflex of BAD. Now, if we continue this kite by extending these two line segments right here, as well as this diagonal, and given our clue, we have this whole angle. This blue angle is 122 degrees, and since we know this bit is 52 degrees, then this other bit must be equal to 72 degrees. Alright, so from the properties of a kite, we know these are equal, and again this the triangle ADB is another isosceles triangle which means this bit right here is 70 degrees. And then therefore we can just calculate this angle BAD to be 180 degrees minus 70 degrees minus 70 degrees, which is 40 degrees. And we're not just quite done yet, because we need to find the reflex of this, which is pretty simple. You can just find that this will be equal to 360 degrees minus 40 degrees, which is 320 degrees. Alright, so that's it for question 6 as well as this video. So hopefully you guys enjoyed this. Please subscribe for more videos, and I'll see you guys in the next one. Goodbye.